Hello everyone, and welcome to this topic 5 of the course Machine Learning in Finance. In this video I will talk about decision trees. And the decision trees are like any machine learning model. It's a tool to fit this regression model. You try to find out what is the regression function f by using a data set. The difference between decision trees and, for example, linear models is that a decision tree allows to model non-linear functions f. In a decision tree, however, there is always a problem of overfitting. The model can do too well on the training dataset, but perform badly on a testing dataset or validation dataset, and therefore we need tools to overcome that overfitting of a decision tree. And we will discuss that in this topic 5, and we will illustrate it with examples in R. Let me start with a simple example. So assume that we want to predict the sales of a lottery in a given region. And we say that the number of lottery tickets that you can sell depends on the population size of that region. The more people there are in a certain region, the more likely it is that you will sell a large number of lottery tickets. So we have a data set at our disposal, and for different regions we can observe the population size and the sales of lottery tickets of last year. And then we try to find out what is the relation between population size and sales. So our target variable, the variable that we try to predict, is y. The feature variable, the variable that we can use to have information about the y, is the population. So the model is y equal to fx plus epsilon, where x is the population and y are the sales. And we start with a very simple model. It's the linear model. So the model where we have an intercept beta 0, and we say that the sales increase in a linear way in function of the x, the population. A linear model, a data set, we can do that in R with the lm function. And I show how you can do that in the separate video on the R coding. But if we take the data, we see that we have 4 different groups. We have this group, we have the red group, the green group, and the blue group. The red line that we see here is your linear model. So what do we see? First of all, we see that inside each group, the data doesn't fluctuate that much. For example, have a look at the green group here. The variation inside the group is relatively small. And the gray horizontal line indicates the mean of your group. So the mean of all the green observations, for example. And what we see is that the means of each group, that seems to behave more or less linear. With the linear model, the red line, we can describe these means. But we cannot really describe what happens inside each group. Otherwise stated, we can predict something with the linear model, but not everything. So we have a data set that has sales and population for a number of observations. We call the LM model in R, and then we get this output. And what we see is that the p-value of the beta 1, the slope of population, is significant, and we see an R squared of 0.9. So it seems that our linear model is a good model. It's able to explain what is happening in the data. Based on the results of the linear regression model, we find that the population is significant. The variable population is important for our model. We get a large R squared value, so that all looks very promising. However, the linear model is not accurate inside a group. If you have a look at the plot with the data, you see that the means of each group, that is lying on that, more or less on that linear model on the red line, but once we are inside the group, that linear model does not really perform very well. So we need to inspect the residual plot. What are the errors that we make with our linear model, and are the errors truly independent from all the rest? What you see here is the residual plot of the linear model. And here we have 0, and it seems that the residuals are centered around 0. So that's good. On average, our model works. However, you see that in the residuals there are still patterns. We see that there are regions where we have always positive residuals and regions where we have always negative residuals. However, if we know that for a given data point, say this one, it's very likely that the residual is positive, then we can exploit that information to get a better prediction. If you know that the residual is positive, well, that's information that you can use to update your prediction. So as long as there are patterns in the residual plot, we can use these patterns to improve our model. So the linear model is not really capable of describing the dataset. It can explain something, the means, but not everything, meaning it cannot explain what happens inside each group. So with that linear model, we can explain part of the relation between our feature variable x and our target variable y, but the data itself is not linear, meaning that there is room to improve the model. And how can we improve the model? Well, first of all, x and y is not linear, but it's organized in groups. And inside each group, the variation is small. So it means that if I know in which group my data point is, then I can predict quite accurately. It's just that I don't know if a certain x is in the black group or the blue group or the red group. What you see here are the sample averages of each group. So for example, if I find a way to determine in which group a certain value x is, I can use the sample means as a prediction. For example, assume I have an x and I know it belongs in the red group. Given that x belongs in the red group, this sample mean of 5,949 is a good prediction. So I want to build a new model that first determines in which group an observation is, and then uses the sample mean as the prediction. Since the data is not linear or not entirely linear, we will switch from the linear model to a decision tree. So a decision tree is a machine learning algorithm that allows to model nonlinear relationships between the feature and the target variables. So what I will do first is I will just apply that decision tree on our data, and then we look at the residuals. And then we want to see that the residuals show less patterns compared to the residuals of the linear model, meaning that the decision tree is better to explain what happens in the data. Then later on in the next video, we will discuss in detail what is a decision tree. So that decision tree will group the data in different groups and then use the sample average to make a prediction inside each group. And that makes sense to use the sample averages because inside a group you have only a small variability. So the main prediction problem is to predict what the group of your observation is. Because once you know the group, there is less variability inside the group, so then the sample average is a good basis to make a prediction. If we implement that decision tree in R, using our dataset, we find this decision tree. So what does the tree tells you? It tells you that first you need to split the population size in two parts. There's one group where the population size is smaller than 11,565 and another group where the population size is larger than this number. So it means that if you look at the population, we have here 11,565, you have here group 1, and you have here, say, group 2. However, if we are in group 1, we have a second split at 4,234. So it means you have this prediction 669 that you use if you are in this group. You have another prediction that you use if you are in this group. The same for this group here. We have a split at 29,000, so it's here. And if you are in this region, we use this prediction. If we are in this region, you use this prediction. So this decision tree makes 4 different groups. You have group 1, we have here group 2, we have group 3, and we have group 4. If we have a certain value x, we first determine using this decision tree, is x belonging to group 1, 2, 3 or 4. If it turns out that x belongs to group 1, then this will be our prediction, 5,949. Based on the decision tree I showed you on the previous slide, we can take every observation in our dataset, determine to which group it belongs using the decision tree, and then make a prediction. Once we have the prediction, we can calculate the residuals. And this is the residual plot. And what you see, I hope, is that there is much less structure in this residual plot compared to the residual plot of the linear model. That linear model showed very clear some patterns, meaning that the model cannot really explain everything of the data, whereas here there is less structure, less patterns, meaning that we can explain almost all the relationships inside the data set, and all the rest that we cannot explain is just noise. Alright, so that was the illustration to show you why we need decision trees, because we want to model these non-linear patterns. So let's now have a look what is exactly a decision tree. So we assume that we have a feature space where we have x1, x2, xp, your feature variables. And the feature space is denoted by R. So R is a set such that each observation that is possible belongs to the set R. So for example, if say x1 is the price of a certain stock and x2 is the price of a second stock. And assume that I use x1 and x2 to predict something on the stock markets. Then the feature space R is equal to R2 plus, because x1 always takes positive values, it's a stock price, same for x2, so any feature vector should belong to this R2 plus. If x1, x2 are returns, then they can also take negative values, then the feature space R is just R2. So in R, the feature space, you have all possible feature vectors that you will encounter. So what is a decision tree? A decision tree segments the predictor space or feature space into different regions using a consecutive number of binary splits. So you take that feature space R and you subdivide it. We want to create groups. A different prediction model can then be employed in each of the subregions. So if we have our feature space R and we know that X is in R. Of course, if we can make a smaller subregion of R, maybe we can predict better in that subregion. Recall the previous example. We had the 4 different groups. Once we know in which group our X belongs, then we can predict quite accurately. And that's the idea of a decision tree. First, create subgroups of your feature space and then predict inside each feature space, each subgroup separately. Let me illustrate that with two examples. A first simple example is a car insurer. And the car insurer wants to predict the number of accidents of a policyholder in a given calendar year. And for each policyholder, you have X1, the age, X2, sex, male, female, the car price, where we assume that the car price is in this interval. We have how many miles you drive per year, and we assume that the miles that you drive is given by this interval. And finally, we are in the US, so we can say in what state is our policyholder living. So assume that the age is somewhere between 18 and 90, then this R is your feature space, meaning that any X for which you need to predict the target Y takes a value somewhere in this space R. And then with the decision tree, we want to segment this space into smaller spaces and predict inside each separate space. For example, a first space could be all males and the other space could be all females. So we divide the feature space in two parts, the males and the females, and we see maybe if I know that my policyholder is a male, I can better predict than when I have no idea if it is male or female. Let's have a look at a second example. In this case, we have a life insurance company that wants to understand what type of households are purchasing a life insurance contract. And in order to make that prediction, we look at two variables. We have X1, how many people are living in that household, and X2, the yearly income. And we assume that this is the feature space. So we have households up to 6 people, and we have a yearly income up to $100,000. The target variable that we try to predict is Y. It's just yes or no. Either you have life insurance or you don't. And we look at a very simple data set with only 8 households. And here you see the data. We see on the x-axis the number of people in a household, and we have the income. And then you see for each observation if that observation has life insurance or not. And for the moment, do not have a look at the horizontal and vertical red line. If we have this data, we have 8 observations in total. We have 5 times yes. We have 3 times no. It means that if I have no idea of the different regions, then I have to predict yes for having life insurance, and then there is a probability of 3/8 that I'm wrong. Okay? However, if you look at this feature space, you can partition this feature space, you can subdivide it in 3 regions. We have region 1, 2, and 3. What we see is that in region 1 and 2, it's very easy to predict because everyone in region 1 has life insurance. If you have people that have a lot of money but not too many people in the household, for sure they will pay for life insurance. If you have people that have a low income, then they will not pay for life insurance. In the group 3, there's more ambiguity. It's not that everyone says yes or everyone says no, but we have yes 1, 2, 3 times and only 1 no. So if I predict in that third group, I predict yes, but there is only a 1/4 probability that I am wrong. So it means that by looking into these 3 subgroups, within each subgroup, I can better predict my response than when I do not have these subgroups. Before ending this first video, let's recapitulate what we did. So we started with a feature space R. Any observation belongs to that R, but we subdivided that feature space in 3 parts. We had R1, R2, R3. However, we subdivide in such a way that if we put all these R1, R2, R3 together, we end up back with R. And we have an observation X. Because of this, we know that X belongs to at least R1 or R2 or R3. With this condition, we state that X can only belong to a single subregion. If X belongs to R1, it cannot belong to R2 or R3. So the union Ri, Rj is always empty if I and j are not the same. Why do we subdivide our feature space? Because inside a subregion, I can make better predictions. In our particular case with the life insurance, in R1, R2, there was no ambiguity of the prediction. Everyone in our dataset was saying yes or was saying no. In R3, there were some who were saying yes, some who were saying no, but I could predict more accurately in R3 than I could in the whole feature space. So with the decision trees, we will find out how we can achieve these subregions. If you have a feature space, how do we subdivide in an efficient way?